Okay guys, I'm supposed to do introductions now, or summations first. I'm going to talk to you about triangles. Two triangles, 1 and 2. I'm going to talk to you about formwork, how the formwork could have been a problem here, and also how the rods being of the wrong length could be an issue. Also, how this, if this is not square, if these aren't square, how this creates an issue. Sorry about my so close to the camera there. If this is not square, this could create an issue. Before I do that, let's talk about some perfect stuff here. Coin. These are elements. You know, these are elements mixed together in a perfect harmony, if you will. I would say perfect harmony because we see them for 30 plus years without any swelling and failure. Of course, we have a penny. This element is copper, and I don't know how pure this copper is, but it seems pretty good to me. It's not failing or delaminating, and we can go back to the 40s with this stuff and 20s, and it seems like they're using pretty good, an element of copper that's pretty consistent. We have copper in here also. It's pretty arse, pretty nice. So why is it not delaminating? What's the math behind that? The two elements are trading off beautifully. So there is magic going on between here. These different elements, electrolysis is taking place of some degree. Oxidation is taking place to some degree. Electrons are being transferred back and forth here, but they're in symmetry, they're in balance. Aha! Now we go to this, balance. I'm going to have, this is very important. We come to 228 where this tension came in here when they tensioned this. So let's establish some working grounds here. We have 4 bars inside here at this point, probably just mechanically done with a ratchet. Nothing like the hydraulic tooling. Probably just a ratchet securing them here and at the bottom, maybe holding it anchored up. So we got 4 pieces of steel holding this from falling apart. We have the formwork from here to here and from here to the ground in place, which will create friction when you're trying to move it. You'll get a friction and resistance. Okay, but that's also something you can judge from. If you see it lift off the form when you're post-tensioning this member, you now know you're creating a camber inside the structure with this, pulling this taut. How can you create a camber? How can you create a camber with that? Well, this is your hinge, is how you would do it. This is just exploring this for you guys. This is the hinge. I'm going to use my shoulder as the hinge, and I'm going to use the shoulder as the hinge as I retract and pull back. You know, this is the anchor, so the anchor point's here. If I could get smaller, I'm going to create this moment, right? I'm going to give you a little bit of a moment, a little bit, right? Just that little bit. That would create a downward force at this point, wouldn't it, by default? But that downward force is stopped by the post-tension cables going across here. So I am met with some resistance, but I have built-in energy, and I like to refer to it as kinetic, not potential. So it's kinetic energy. It's always working, I'm saying. It's always there working. It's part of the formula now. So it's there like that, holding. I'm not going to do that, right? I'm going to do this. I'm there holding. When you start adding all the other forces, all the other forces have to also now to work. They've got to come past me, and I'm giving them some resistance to work past. And when you finally release the tension in this one, all the other ones also that are interacting with my muscles here, interacting with my tendons, my cables, my rods, when I relax, they all relax also because they don't have a load off of them. When they're doing so, this is where I think that the whole drama happened, including that that part of my shoulder girdle was part of this 12. And when doing so, it now relaxed, and the loads here gave a downward force that can simulate the shear that we see in the bottom. Sorry about that. Sorry about that. I'm going to have to loosen this up and do it live. That we see in the bottom. Yeah, really? I just tightened it by chance. So that we see in the bottom of that we see in the bottom down here. This is told, everyone's referring that these forces are coming down here, pushing through because it slipped. So not punching, but sliding. But they double dipping, some of these clowns. They say it's a punching shear, and some of them say it's a sliding shear. Which one is it? Is it punching and sliding? Okay, well we just lost. You just told me it became sliding because I had a detension A, and I call A and B. So that's how I got the sliding effect. I lost the friction ability of the clamping force of this at this point. So when I released it, I'm able to slide now. So that's sliding at that point. That would just knock 12 off. But they magically have it not only knocking 12 off, but redirect and creating a shear effect down here. So it only, when I say redirect, that's because the deck goes out to here, including that blister that holds 12, this part of 12. That's part of 12 in the clamping force. The clamping force is only in the blister. It is not in 12. 12 sits on top of the deck, right, along with 11. They're stating when you release the clamping force, part of it is theorizing or extrapolating, and I'm going to extrapolate this way. So that you release the force, this can create a sliding effect of 11 pushing 12 off. It's great. We got a video though that doesn't show 12 being pushed off. So we don't have that. We've got a member that's broken down here that doesn't have the capacity to push 12 off. You know, it's like me having broken fingers trying to push somebody. It's not going to happen, isn't it? The pain's going to be felt back here, and I'm not going to be able to push with these fingers. Same thing here. This is all broken up at this point. It doesn't have the capacity to push off the thousands, tens of thousands of pounds of weight of this guy, or forces, so to say. The canopy does have a load here. There is a cantilever here. They're not addressing this cantilever effect. So what? It's post-tension and you're calling this a zero-force member. It still has a dead load. It's 30 plus feet long across here. It's not just cantilevered out. So therefore it has a downward force that's coming down here. Of course down 10 also as they divide up however these forces resolve themselves with the post-tensioning. Because it's not just down the middle at this point, cantilever or 3/4 out. Because the post-tensioning has the ability to keep things, to allow a cantilever, it can allow a much longer cantilever than typical. So I don't know where, you know, the calculations of it, where the dead loads would be. Well, from here downwards. This is a joint here, and we don't see any connection of this joint. Let me make sure. We don't see any locking of this joint short of the trumpet area of the longitudinal cables here, and it's not much to hold on to. We do have what appears to be this shear in the back of what I call the girder, diaphragm girder in the back. It's a diaphragm, but in this case I'm looking at it as a girder. That some assumptions were wrong, that when they were load testing, for example, that assumption was wrong, that it made it to 40 days as is, because I don't think they removed the tension of 2 and 11 in the load testing area. And they also possibly had it fully shimmed in the load testing area. If not fully shimmed in the load testing area, then it was similar to this build here. As you place it, this clearly would show that the failure is in B, not in A. A is a contributing factor, but B, the top one, losing its clamp force, allowing this, again, this dead load of this to create a shear here. Now they talk about no reinforcements back there. Well, none were somewhere when the plans got changed also by FDOT's suggestion, and then Berger and ultimately Denny Pate changing the plans, that this was lost in time in how the interaction was. It was given not as enough respect as it could have been, not just as a cantilever, but it would have shown that this design at the end needed support underneath of it. And it needed something, support underneath it, to stop the shearing effect in this girder. Now they're stuck in these other forms like engine tips, just going all around this, and they're stuck recycling it because they don't. Their brain, part of their stupid brain, their brains are stupid because they're stuck, and but part of their stupid brain is also knows that it's wrong what they're saying. So it's trying to resolve it by asking the question over and over again. They're stuck in a cycle, and that's like a PTSD thing. They come with a conclusion, but then the brain loads subconsciously that it's wrong, that everything they're saying is wrong, and so it keeps making them go after it over and over again. Whereas I, on the other hand, are trying to find multiple ways this could fail, and I keep going, I keep searching. I need to resolve all of every single bit, and when every last crack is resolved in my way of trying to find the failure path, then that it will be the failure path, because it will explain every single thing. That's why I need more data. For example, did they put this over here, or so I can start eliminating? Did they have it in the staging area? Did they have temporary bracing underneath it here? Did they temporarily remove 2 and 11 during post-tension, during the sampling of 40 days over there? I don't think so, because the path that the schedule that they post-tension this is different. Did they do it in steps, 50 and 50 and 50 and 50, when they first initiated it, and also when they detensioned it, and also when they pre-tensioned again, when they retensioned again on the 15th? Did they do it in cycles for real? And that's that data we can get from the crane operator as a neutral person, if the crane operator would be willing to be neutral and state that he repositioned the crane multiple times. Could it only been one crane position and they were able to swing, the crane operator just had to lower it? That's still repositioning. Could they have been able to swing with the manpower, move it from A to B? This means we don't need that statement that I need to see the crane operator moving it 12 times. So you can see that I attack myself with some of my statements. This is how my brain thinks. It's able to figure out ways that it's always trying to find the truth. And with that said, it checks its biases, and it makes all conclusive files, my brain makes all conclusive files a bias. And it says, how can you prove that it's being biased? For example, the crane operator, I stated that needs to move it maybe 11 or 12 times. That's a conclusive file. Now I say, well, that's a bias. How can I make it happen otherwise? Well, I need to move the equipment. Okay, then maybe I can move it with manpower. And so now you see how my brain works. Now let's go to the 2 triangles. And when I finally can come up with a system from A to B, there is no bias anymore. It's just the way it could work, period. We know 100% the bridge failed. We just need to find out how it failed. We add all the elements, including adding post-tensioning, what took place after that, of course the calculations. But at this point, calculations are all off because we're at the 15th when the failure happens. Their calculations don't make sense because they didn't deduct for, they accounted for things that are already in failure mode, and it's a broken arm. It's like, how much strength do I have in a broken arm as I present you a broken arm? You're like, you know, that arm is useless at this point. And you're like, well, it's still alive. Still got some flex to it. Look, I can still move my fingers. You're like, yeah, but it's not, its intent is no longer functional. You can't lift up the 80-pound rock anymore with that broken arm. I'm like, no, but it's something. But these engineers, including a few idiots that write me, keep telling me it's discounted, it doesn't count, you can remove that, or the one idiot, Andrew, stating that it's still fully functional. Number 11 is fully functional with a broken arm. So I found Andrew to be a trigger to me, and I blocked him. He's my 3rd person I have blocked on YouTube. One is a music channel, and the other one is AVI for his stupid comments, such as his advertising on my channel. He literally came there and I was asking people to come over to visit his channel. I'm like, you got 1 million people, don't you? Why are you asking people to come visit your channel? And so that's why I felt free to attack him back. So anyway, that's just, I have no choice. I attack back. I don't pretend like I don't pretend to be passive. If I attack back passively, it's still an attack. I don't pretend that we can be passive, that it's all a form of attack. Back to this, and you know I love psychology, that's why I introduced this part of your behavior and your reactions and your talking. So now, on 228, we have tension in here. If you think of these 2 triangles, how do I get tension in here? Well, I would need this area to weigh more than this area. I would need this area to go up to create tension in here. Or conversely, I would need this to be 100% stable. This area, this longer deck, to go down. This would create cracks in here. These cracks appear to be nothing, right? They're fine cracks. But you forget that these have 4 bars in them, post-tension bars in them. If you were to loosen those bars, those cracks would open up. There's not, that's theoretical. I think not. I think that they are clearly indicating that this is not 10 pounds we have on this deck. Also, I have, going back to that statement, we have people like Andrew telling me, and everyone else telling me how much this deck has per linear foot. I think he said 10.88 kips per linear foot. Let's call it 11 kips per linear foot. I wrote him that that's the stupidest asinine thing I've ever heard, to determine that this bridge has 11.88 kips per foot. Why is it so asinine for any engineer to say that? It's because if that is true, the deck wouldn't fail. It wouldn't fail, period. Because this is the problem with a lot of these engineers. They don't have ability to use their brain. You just told me it's that much per foot. This is your bias now. This is why you can't come out of it and find that where you're going wrong. If that's the case, this bridge can take that much per linear foot. As you break it up per linear foot, it can take that much. But that was not true, because at this failure, it had to have more than 11 kips per foot, rather. I mean, per linear foot this direction, not per square foot. And so, if that's the case, this bridge section wouldn't fail. If that's the case, this wouldn't fail, because now you're only telling me I got to put 11.88 kips here, and I got 11.8 kips here per foot. So this stops that. 11 pushing 11 is done. It cancels it out. Can't get a failure here because, well, it's 11.8 here, it's 11.8 on this side. In that case, it could fail randomly anywhere then, if that's the case, because it's all equal, they say. That's the crap engineering brains, and I find most of these engineers to be lacking. I find a lot of engineers not to have the intelligence of maybe 5 or 6 of you guys who watch here. I find you guys amazing, and some non-engineers here I find amazing. On the engine tips forum, I find the computer guys friggin' amazing. A couple of electric guys are way off base. A couple of them are really good. But the computer engineer guys, I find them to be amazing. I'm not supporting they're correct, but I find that somebody in computer engineering has some great logic, man. Their logic is right, is great logic, but it fails, ultimately. Because they're stuck in groupthink at that point. They then can't come out of it. So how do we get tension here? But we know that it happened after they tensioned this one, which means they put it in compression. How do we get tension here? If you're putting this in compression, you have 2 anchor points, one here and one here. You've got to choose which one is acting as a hinge. Which one did it? So if you choose the canopy as a hinge point, and that's the point that would create a reaction, you've got it lifting up. You have this lifting up, and this triangle acting as one. Hey, Bruce, I'm just showing everybody. Let's show you Brucey. Brucey. Oh, sorry, Bruce. That's Bruce's and Bruce Lee. So then you have this acting as an individual triangle, and the hinge point, this would be lifting up, creating tension here. Doesn't work. Putting this triangle this way, and here's the anchor point here, and now you create a compression, and if this could create a rocking force like this, just look at this single triangle, and if it could turn like that, like this, if this could lean back, all of this together, right? If this could lean back like that, you would get tension here. And when you do that, look at my shoulder as it kicks in a little bit. It creates detensioning here, compression in this direction. So this would take away some of your longitudinal post. It would shrink. In theory, it would shrink your elongation, making this not as, you wouldn't have as much elongation as you think. So the cracking, you're doing that action there. It's all interacting. It's all connecting. It's all connecting. This crack here indicates that this dead load went down. To go down. So how else do I create a force going down? Well, when I put tension on compression on this, it is an anchor point. This anchor point can also do that. At some point it's directing down. These are tension cracks, not compressive cracks, right? So it has the ability to push down. But if the initial reaction was it pushed down, lowered this deck, and this recovered, if you will, I don't know how exactly, when he photographed and what time, if this recovered back, its elasticity, if this became more flat than this one, deflection is here, we get opening here. We're limited again to the torque applied to the clamp force applied to the 4 bars in here. Or conversely, if this took a crown, went up. So if this is flat, and when you add compression in this created this reaction like this. This creates a crown in the canopy. A slight crown. We're talking. I need a resolve. You need to come up with the tension we know to be in 10, as reported by the CEI. So a slight crown would do it. A slight deflection would do it in the deck. Those are your two choices. You get a crown or a deflection from post-tensioning to an 11. Looking at A inside here, this comes back to the deck. Deck only, not outside. And so does B. So does B come back to the deck. And in this little bit of blister that's tied to 12 across a joint. Across a joint, this blister, if I stand out here with a hammer and I start pounding at the blister without it being in there, I can break apart the blister. In theory, this would be okay by itself, as long as it's supported underneath. I can destroy the blister, and 12 is still 12, minus the overhang, 10-inch overhang here. So it has the shear force of 10 coming down. Looking at it from the end now, not from this direction. All right, let's look at it from the cross section. Hey, Georgie, Bruce. The shear would be, if this are the ends, would be out on a 45 like this. If we just look at 12 alone. So it's coming back in this plane here. That does dissect. If it's coming here, it does come right to that metal, to the top of 11A, top of that post-tension rod. It does cross-section that. And then we have the inside this, in a cross-section, and my scale was off here. It cross-sections it also by the PVC pipe, the 8-inch pipe. That gives it this total break. It only has to break that limited amount between the deck and the top of 11, the steel 8-inch by 8-inch plate. It's not much for it to dissect there, the loads here from 12. The rest of the shear factor would come out into space pretty much, out to this direction. Or would it? Or would it? That's if I count the end, the outside of 12, which is 10 inches off the deck. But that would be wrong for me to do that because the loads the deck is another 10 inches inbound. So coming 10 inches inbound and putting the shear force at the edge of 12, with the overhang giving an imbalance, if you will, meaning you're creating more shear on the outside, more shear force in the outside than you are in the inside. And your connection between these two are only the rods at this point of B to hold these two together.